Hi class, this is part 2 of the Module 8 video for topic 8.2 and 3. This is really about what we call hypothesis tests, as you can see for our heading here. And I think that you will find a lot useful in terms of understanding your research papers here, because most research papers deal with hypothesis testing. All right, and I'll try to mention a few things that will help you in terms of thinking of your research papers as we go on. Okay, so let's start off with our situation, and you might recognize this scenario from your test. A Pew Research report states that 10% of all 18 to 24-year-olds in the U.S. are enrolled in a community college. A survey of 240 18 to 24-year-olds in Florida indicates that 36 of them are enrolled in community college. Does the survey indicate that the proportion of 18 to 24-year-olds enrolled in community college in Florida is different from the nationwide figure? So let's take a look. So the first question is, does the survey support a yes answer to the research question? Well, P hat is our sample proportion, which is 36 out of 240, or 0.15. So 15% of the sample of Florida students, Florida young people, 15% are enrolled in a community college. And the national figure is 10%. Well, this would support a yes answer to the research question, because 0.15 is different than 0.10. So 0.15 is not equal to 0.10. The sample proportion for Florida is different from the nationwide figure. So does that mean then that the number for the population in Florida is different? Well, to answer that question, we have to think about what are reasons the survey might have gotten results to it that it did. We're going to leave out poor sampling methods and things like that. We're going to say, suppose the sample was done well. Well, really, there's two reasons. Reason one is because of simply sampling variation, or random samples, or sorry, random chance. So that means, so another way of thinking about that is different samples give different results. So in other words, it just might be just pure luck that our number is different than the nationwide number. We don't know. If you take a bunch of different samples of size 240, you get a bunch of different answers. All right. Well, there's one other reason, and that's that there actually is a difference. There is a difference between the Florida proportion and the national proportion. So the difference between our p hat of 0.15 and our nationwide population proportion of 0.10 could have occurred due to sampling variation, or because the number in Florida actually is not equal to 0.10. All right, so the first step then to actually determining which of those two it is, so that's what we want to do now. Is it number one or is it number two? What's the reason why we got the difference? Okay, what's the most likely reason? So now we determine what we call our hypotheses. We have our null hypothesis, HO, and our alternative hypothesis, HA, and some other places you may see that given as H1 rather than HA. And these are always about the parameter in question. Well, let's define our parameter then. Our parameter is P, the proportion of all, so it's a population proportion. What population is it? All 18 to 24-year-olds in Florida. The proportion of them who what? Who are enrolled in community college. All right. So both of our hypotheses are about that proportion. So you got a P here and for HO and a P for HA. And the HO is sort of your baseline. Your what if it's what would be true if number one was the answer. The only reason for the difference was random chance. Well, then the proportion in Florida would be equal to the nationwide proportion. Okay, so you might think of the null hypothesis as being a statement of no difference or no change, no effect. Sometimes we think of it as one of those. In this case, it's always an equality. So always equals. Okay, the alternative hypothesis is always inequality, and it's what would be true if number two is correct. And it says there is a difference between the Florida proportion and the national proportion. That would mean that P is not equal to 0.10. Okay, so this is always an inequality, which could be less than, greater than, or not equal to. All right, and that's sort of what we're trying to test. We're trying to test whether that's a more likely explanation. Right, so those are our hypotheses, the null and alternative. Okay, so let's look at the next page. So now I want to check my assumptions and gather data. So the assumptions are we need to make sure, so this time we do have, unlike with confidence intervals, this time we do have a number to use for P, and that's the number in my null hypothesis. So I need to check that I have a normal distribution. So I need to check NP, which is 240. I check my sample size times P, which is 0.1. That's 24. And I need to check N times 1 minus P. Well, that's going to be even bigger because we're going to use 90% for that. So that's 240 times 0.9, which is equal to 216. These are both of these are at least 10. So the normal distribution holds, and that's very important that we have our normal distribution. Okay. All right, so that's our assumptions. That's what we need. Also, data were gathered randomly. So you need to make sure you have a representative sample, and since our data were gathered randomly, we're good there. So you need to double check that. And then the gathering the data is just your sample data, and we already have that. So the data is our statistic of p hat is equal to 0.15. Right, now we want to assess the evidence. In other words, how unusual is that sample proportion? And if it's really unusual, given the null hypothesis, then it lends credibility to the idea that the reason for the difference is because there really is a difference, not just sampling variation. So, well, we have a normal distribution, so let's draw a bell curve. And the mean, so that's our sampling distribution. The mean of that sampling distribution is our population proportion, our assumed population proportion if there's no difference. So in this whole hypothesis test, we're assuming that the null hypothesis is true. So the mean is 0.10. And then we're going to plot our 0.15 here. And so we'd be looking at how unusual is a result like 0.15 or greater. So I plotted over there to the right. And then I also actually, because I said not equal to instead of, oops, I didn't mean to do that. Because I said not equal to instead of specifically greater than, I also need to consider the left tail as well. It's supposed to be symmetric. I didn't do a very good job of drawing a symmetric curve. So what I need to do is find the shaded area. The shaded area tells me how unusual P hat is if HO, the null hypothesis, is true. That is, that P is equal to 0.10. Okay, so how do I find that shaded area? Well, finding the area under a normal curve is a normal CDF. And that right tail, the lower bound is 0.15. The upper bound is infinity. The mean is 0.10. And the standard error, we use that formula. And this would actually be the same standard error from the test, which I'll be emailing you shortly. But there's the standard error formula. The square root of P times 1 minus P all over N. Okay, so let's bring up the calculator. I already have my calculator ready. So I hit second and the vars key, and I do choice 2 for normal CDF. I do 0.15. Oop, I missed the 1. 0.15, a comma, and a big number. Okay, and then a comma, and then 0.10. I could just do 0.1. And then square root of 0.1 times 0.9 divided by 240. And I hit enter, and I get about 0.005. So I'm actually going to do 0.0049. But it actually, because I have to look at both tails and the curve is symmetric, I'm going to double that. Okay, so let's bring my calculator up again and multiply by 2 times 2 equals 0.0098. That makes sense. 49 times 2 is 98. So approximately 0.00, let's make that not look like a 6. 0098. And we call this number our p-value. So we use a I'm going to write, to not confuse it with our population proportion, I'm going to write p-value. All right, and basically what the p-value is it's the probability we would get a sample proportion in this case, or a whatever your statistic is, at least as far from 0.10 as the one we did. So a sample proportion at least as far from 0.10 as p hat equals 0.15, at least as far, so at least 0.05 away from 0.10 would occur about 1% of the time if p actually is 0.10. If the population proportion is 0.10 and the sample size, I should have said, let me add here over here, because the sample size is important. That would change things. And a sample of size 240 here. Okay. So pretty darn seldom, only about one sample in only about one sample in 100, a little less than one sample in 100, would do this, would be that far away. So let's go back. What are our possible reasons for our difference? Either sampling variation, well, it doesn't happen very often due to sampling variation, or there actually is a difference. So chances are there's a difference between the percentage in Florida and the percentage nationwide. Okay, so that's where we're going to go to. So our conclusion. Well, to make your conclusion, you have to say, well, how unusual does it have to be? Well, ours is pretty darn unusual, but we usually have to say, we have to decide what we call our level of significance. And that is, how unusual does it have to be? Less than how often would it occur by chance? So we need to choose a level of significance And usually that is either 0.10, 0.05, or 0.01. Those are the most common, of which 0.05 is the most common. And but ours occurred even less. So that means whichever level of significance you choose for your test, we're saying that if the results that we got are unusual enough to occur less than that % of the time by chance, then it's probably not chance as the reason for the difference. So in this case, even if we chose the strongest level of significance and said it has to happen less than 1% of the time, ours was a little bit less than that, and so that's okay. All right, so in this case, we compare the p-value to that. So oh, by this way, this uses the lowercase Greek letter alpha as the symbol. So if the p-value, spell value correctly, if the p-value is less than the alpha, then we reject the null hypothesis. In other words, we're saying the difference is not just due to chance, that the null hypothesis is probably wrong. But if the p-value is greater than alpha, then we fail to reject. And that's important. We're not saying that the null hypothesis is true. We're just saying we don't have strong enough evidence to conclude that it's false. In this case, this is the case. Because no matter what alpha we use, 0.0098 is smaller than all three of these numbers, 0.10, 0.05, and 0.01. So we're in this case, we're going to reject the null hypothesis, and we can thus now write our conclusion so that we can say what the final result of our hypothesis test is. And we can say there is enough evidence to say that the proportion of 18 to 24-year-olds, I'm going to abbreviate here, in Florida who are enrolled, and I'm going to abbreviate again here, community college, is different, and in all likelihood greater based on our sample proportion, than 0.10. And then I always like at the end of my statement to put my approximate p-value, and here you can write, well, I'll actually write p-value again, so not to confuse with our proportion. P-value is approximately 0.0098, and that's your conclusion. If the p had been greater than alpha and we had failed to reject, you would have only had to say there is not enough evidence, and everything else in that statement would have been exactly the same. All right. I'm going to hold off on the confidence interval for just a moment to do two things. First of all, I'm going to show you can actually get that p-value directly from the calculator without having to do a normal CDF. Let me show you how you do that. And what you do, give myself a little space here, is you take your calculator and you hit this. Let me clear out the screen. You hit the stat key and go back over to test, just like we did for confidence intervals. And you're going to do a 1 prop z test, number 5, because it's for a proportion. All right, and P0 is the population proportion that I assumed in my null hypothesis, which is 0.10. I hit enter, and it just changes it to 0.1. The X is the number of successes in the sample, which it said there was 36 of the sample were enrolled in community college. The N is the sample size, which was 240. And then the next line, the prop, is your alternative hypothesis. In other words, do we believe the proportion is not equal to 0.1, less than 0.1, or greater than 0.1? Well, we used not equal to because the actual statement was different. And that doesn't imply a direction. And then I click calculate. And there's my p-value of 0.0098. Almost exactly what I had before. All right, so let me write it and let me do screen captures and put them in these notes, which I will post. I'll try to do it this evening. Okay, so I go to stat and tests, and I go down to stat tests and go down to 5. So let's screen capture this, put this in our notes. Make it a little smaller. There we go. And then let's do the next one. And then we hit enter on number 5. We'll go down and hit calculate. I didn't mean to hit enter. All right. I'm going to do a screen capture here. Okay. All right. There we go. And then lastly, what your results page looks like. Hit enter. And we let's screen capture this. Put it in our notes. Bring them over here. All right, and then I'll write into these notes what I did. I went to the stat button, and then the tests heading, and then number 5, 1 prop Z test. And then this is here, this is from HO. This is successes. Sorry, I know that's hard to read. And this is sample size. Go. All right. So that's how you can get that directly from the calculator. All right. And then it says calculate and interpret the 95% confidence interval. I'll just do the calculation and just say what the interpretation is. But to do the calculation as a review from what we did in the previous video, you go stat and tests, and you scroll on down. It was letter A is 1 prop Z interval. So it's the exact same first part, but instead of a test, we're doing an interval. And note that the 36 and 240 are still there. We don't have to change our confidence level because that's at 95 already. So I don't actually have to enter anything. I just go down to calculate and calculate. So we see 0.105 and 0.195. So that's the most plausible range of values. And notice that that range of values excludes 10%. So in other words, it kind of makes us, even that confidence interval makes us doubt that the value in Florida is equal to 10%. Okay, so I'll say 0.105 to 0.195. So there's our confidence interval. So we're pretty darn sure that the population proportion in Florida is somewhere within that range, meaning it's probably different from the national figure of 10%. All right, so that's the bulk of it. Let me bring this, let me move this up real quick, because every hypothesis test follows those steps, step 1, 2, 3, 4. But I do want to mention one other thing, and that's that, remember that 1 and 2 are our possible reasons for the difference between our sample data and our potential population proportion. We could have made the wrong conclusion, okay? So it's possible, let's see here. It's possible that, even though the data supported otherwise, that the Florida proportion is 10%. Oops, that's right, proportion there. That the Florida proportion is 10%. We got a result that would happen by chance a little less than 1% of the time. But that isn't never. That's a little less than 1%. So it's possible that we just got a really unusual result. So in that case, then we made an error. Not because we did something wrong, just because we got unlucky with our data. So if you reject the null hypothesis, even though it's true, then you made an error. The other direction is perhaps there is a difference, but the data aren't strong enough to show that difference. Then you would make an error also. So, so we have possibilities. We have HO is true, and we have HA is true. Okay, so HO is true means differences from random chance. Basically is what that means. If HO is true, any difference we observed is due to random chance. I'm going to write small here to fit it in. And if HA is true, that means that the difference is real. Okay, and over here, so this is the truth, and then the two things we might have done were reject the null hypothesis, or we fail to reject the null hypothesis. All right, well, if we rejected the null hypothesis and the difference was real, then we did the right thing. So that's correct here. And if we failed to reject the null hypothesis and the null hypothesis was true, we also did the correct thing. That's right here. Well, if we rejected it, even though it's true, so in the example here, that would mean we said that the difference is real, even though the Florida proportion is actually 10%. We just got unlucky from the data. We call that a type 1 error. And then if the data had not been strong enough to reject, even though the alternative hypothesis was true and we should have rejected, that means we would have made a type 2 error. So you need to keep that in the back of your mind, that it's possible that your conclusion was an error. But that doesn't, again, an error, your conclusion being an error doesn't mean you did something wrong in the hypothesis test. It just means that the results of the data were such that your luck led you to make the wrong conclusion. All right. Okay. I'll set up the proportions on this, the hypotheses on this problem, and then I suggest that you do it by practice, and then look at the other. I'll leave the old notes up as well, so you can look at the more detailed notes. The CEO of a large electric utility claims that 80% of his million customers are very satisfied with the service they receive. To test this claim, the local newspaper surveyed 120 customers using random sampling. So that's good. You got random sampling. Among the sampled customers, 75% say they are very satisfied. Well, that's not 80%. That's less than 80%. Based on these findings, can we reject the CEO's claim of that 80% of the customers are very satisfied? Use a 0.05 level of significance. I don't know, but let's set up our hypotheses, and then you use the calculator to get a p-value and test it. All right, well, the null hypothesis would be that he's right, that there is no difference in this sample. So that would be that p is, p is equal to 0.80. But if he's wrong, we don't really care. We don't really care if it's greater than it. So we're not going to say different from. If he's wrong, it would be the case that it would be less than 0.80. Okay, and so what you want to do is use the use the calculator to define a p-value and see if that p-value is below that 0.05 level of significance. Okay, that wraps up part 2 of the video. I hope these videos were helpful, and I will talk to you in the Monday evening question and answer webinar. Have a good weekend if you're watching this during the weekend, and I will talk to you soon.